Okay, number 32, continuing on with logarithms. So we want to isolate that n, and that n happens to be an exponent. So anytime you see a variable in as an exponent, there's a very strong possibility that you might be using logarithms. You could be using something else, but the other something else, like in this case, would be trying to rewrite 9 and 70 to both have the same base. So if that doesn't work, 9 can only be written as 3 squared, or 9 to the first, and we can't write 70 in terms of 3 to any power. So that's where we know we're going to have to use logarithms. Okay, so again, like we talked about in the last few problems, we have a base of 9, so we're going to take log base 9 of both sides. Those cancel out, and n equals log base 9 of 70. All right, let's see, number 33. So you guys are seeing these log problems go fast if you're prepared and if you know what you're doing. If you're not prepared and if you don't know what you're doing, they're going to take you probably a lot longer than they should. Okay, so here we go. Log base 6 of 2x minus 4. You can read the problem on your own. We have a base of 6 on both sides. So again, both sides get a base of 6. Those cancel out, and we're left with 2x minus 4 equals x. Basic algebra problem. So if we subtract 2x from both sides, negative 4 equals negative x, and then divide by negative 1, so x equals 4. Super easy. Okay, let's move on. So let's do number 34. So here we go. We've got 16 to the 3n minus 1 equals 64 to the 2 minus 3n. So here we go again. We have variables in as exponents, but this time we have two numbers that can be written with the same base. So 16 can be written as 4 squared. We still have that 3n minus 1. And 64 can be written as 4 to the third power, and we still have that 2 minus 3n. Okay, so this is an example of where logarithms, while they would work, are not really the most appropriate or efficient way of solving this. Okay, so we can take log base 4 of both sides. You don't really need to do that. Once we have the same bases, the exponents are logically, by deductive reasoning, they're equal to each other, but if you like to get in the habit of doing that to cancel stuff out, some of us are really into canceling things, which is awesome. Not necessarily needed at every step here, but you can use that if you want. Okay, so here we go. We're going to distribute, so we get 6n minus 2 equals 6 minus 9n, and again, we have just a basic algebra problem to solve here. So let's add 9n to both sides, and let's also add 2 to both sides. So we get 15n equals 8. Good, you can still see that. And then we're going to divide both sides by 15. So n equals 8 15ths. Pretty easy, right? Okay, let me get another piece of paper here. Number 35 needs a little bit of space here. So 35 is, what is x minus 2 to the 5th in expanded form? So some of you have very logically just taken x minus 2 and actually FOILed it out or multiplied it out a bunch of times. You're welcome to do that if that works well for you. But we actually did learn a way that saves a little bit of time. It's still a little bit time consuming, but something that is a little bit more efficient. Okay, so 1, 5, 10, 10, 5, 1. Okay, so remember Pascal's triangle. All of these coefficients represent the coefficients of a plus b to the 5th power. Okay, so that's what we're going to use, all right? Let's actually do a plus b to the 5th power. So we have a coefficient of 1, then 5, then 10, then 10, then 5, then 1. And we're going to put plus signs in here. And remember, the way that we construct this is we start with a to the 5th power on the first one. And then we decrease the a's by 1 as we go left to right until we have no a's at the very end. Now, when you have a blank space at the end, you take the second variable in the term, which is b, and that gets a b to the 5th, and we reduce those by 1 as we go from right to left. So b squared, b, and then no b's. Okay? So a plus b to the 5th is 1 times a to the 5th, or a to the 5th, plus 5a to the 4th b, plus 10a cubed b squared, plus 10a squared b cubed, plus 5a to the ab to the fourth plus b to the fifth. But we're not looking for a plus b to the fifth. We are looking for x minus 2 to the fifth. Actually, let's put that down. Okay, so what we're going to do is we're going to take x and plug it in anywhere there's an a. We're going to take -2, the whole -2, and plug it in anywhere there's a b into this whole expression. So we're going to take x, plug it in for the a's, and we're going to take -2 and plug it in for the b's. And then we're going to simplify it all out, and then we'll be done. Of course, if you would like to multiply x minus 2 to the fifth out a bunch of times, you're welcome to do that too, but this is a little bit more efficient. -2 squared, 10 times x squared times -2 cubed, 5 times x times -2 to the fourth, plus -2 to the fifth. All right, so let's go through and simplify each one of these. First one, x to the fifth. Whoops, can't see that. X to the fifth is just x to the fifth. Then we have 5 times -2 is -10, x to the fourth. Then we have, so go through and do the coefficients or the numbers first by themselves. Deal with the letters of the variables. Afterwards, do the numbers first. -2 squared. -2 times -2. Positive 4 times 10 is 40. So 40, and then x to the third is x to the third. -2 to the third is -8 times 10 is -80. X squared. Then we have -2 to the fourth. So that would be 16. And 16 times 5, that would be 80. So 80x, and then -2 to the fifth is -32. Right? So believe it or not, that does take less time than going through and trying to multiply x minus 2 to the fifth out over and over and over and over again. Okay, so next video.